Can you guys see my screen? Engineers?
Yes.
So in summary, when you have a Cauchy-Euler equation of second order ax squared y double prime plus by prime plus cy equals 0. For the three cases, for case 1, when you have real distinct roots, then the general solution is c1 x to the m1 plus c2 x to the m2. Real distinct roots. The general solution is y of x equals c1 x to the m1 plus c2 x to the m2, where m1 is different from m2. If you have complex roots, maybe I can give an example to illustrate this so that it's not as strange. Find the general solution of x squared y double prime plus 3xy prime minus 3y equals 0. Clearly it's Cauchy-Euler because the coefficient of y double prime is x to the power 2, so the power matches the derivative. The coefficient of the power of x, the coefficient of y prime is 1, the coefficient of y is 0. So to solve this, you assume a general solution y of x equals x to power m. For you to be able to come up with the auxiliary equation, then you have to differentiate your y so that you obtain your two derivatives, y prime as well as y double prime. Plug them in the differential equation, do some factorization, and then you end up with the auxiliary equation. Y prime is, use the general power rule, pre-multiply by the power m, then decrease the power by 1. Y double prime is the derivative of the first derivative, so we have m times m minus 1, which is the new power. We decrease the power by 1 again, so m minus 1 becomes m minus 2. So we plug in these two, the function y together with its two derivatives in the differential equation. X squared y double prime becomes x squared times m into m minus 1 into x to the m minus 2. So we'll have x squared times m into m minus 1, x to the m minus 2, plus 3x times y prime is m, x to the m minus 1, minus 3 times y is x to the m. We need this to be equal to 0. We group together the m's, so using exponential laws, m into m minus 1 times x to the 2 x to the m minus 2 plus 3 m x to power 1 x to the m minus 1 minus 3 x to the m equals 0. M into m minus 1 x to the power 2 times x to m minus 2 becomes x to power m plus 3 m x raised to power m minus 3 x raised to power m equals 0. We factor out x power m, it's common, x power m into m times m minus 1 plus 3m minus 3 equals 0. Now we have that x power m cannot be equal to 0, therefore our auxiliary equation is m into m minus 1 plus 3m minus 3 equals 0. Let's distribute the m in the first bracket. We'll have m squared minus m plus 3m minus 3 equals 0. This is our auxiliary equation or characteristic equation. So we solve the auxiliary equation to obtain the roots. M squared minus m plus 3m minus 3 is the same thing as m squared plus 2m minus 3 equals 0.
Excuse me, madam, could you slow down a bit?
Is there something you've missed such that I either need to scroll up?
Yeah, scroll up. The auxiliary equation. Yes, there.
Okay.
It's fine.
When you solve m squared plus 2m minus 3 equals 0, what do you find? We need the roots.
One and negative 3.
So we have m equals 1. We can say m1 equals 1, m2 equals negative 3. Clearly 1 is different from negative 3, so this is like the two roots are real and distinct. So y1 will be x to the m1, which is x raised to power 1. y2 is x to the m2. m2 is 3x minus 3. To form the general solution, we use the principle of superposition. The general solution is c1 x to the m1 plus c2 x to the m2. Or simply c1 y1 plus c2 y2. So this is going to be c1 x to the 1 plus c2 x raised to minus 3. This can be rewritten as c1x plus c2 divided by x raised to power 3.
Could you scroll up? You've gone a bit fast.
Is that okay?
Up kidogo, up kidogo. There. Down. Down.
That concludes this question. We now move to complex roots.
Okay.
When you have complex roots, I'll just give the formula for the general solution. The general solution is y equals x raised to alpha times c1 cos beta ln x plus c2 sin beta ln x. If you have repeated roots, for you to be able to determine the second solution, you use reduction of order. We will not be able to go through that. But for repeated roots, y1 is x to the m1, y2 is x to the m1 times natural log of x. The general solution is the linear combination of these two. Y is c1 y1 plus c2 y2. Y1 is x to the m. Actually, it's just x raised to power m because it's a repeated root. You don't have to call it m1. It's just m. m1 is equal to m2. It's equal to m. c1 x to the m plus c2 x to the m times natural log of x. We can now go back to solving our Laplace equation in polar coordinates. We had our two separated equations. Back to solving r squared r double prime plus r prime minus kr equals 0. That was the first equation. Theta double prime plus k theta equals 0. So remember, we arrived at these two equations by setting the two equal to some constant k, and k has three possibilities. K can be negative, it can be positive, it can be equal to 0. So we can start with case 1. We investigate the case where k is greater than 0. Remember, I told you the surest way to tell that a constant is positive is by use of the square function. The square function is always positive. So we set k equal to some index, say lambda squared. So if k is equal to lambda squared, we substitute k in our two equations with lambda squared, and then we proceed to solve. So solving equation 1, we will have r squared r double prime plus r prime minus k times r. So k is lambda squared. We have minus lambda squared times r equals 0. So this is Cauchy-Euler in the variable r. We were dealing with the variable x, so we only need to replace x with r. In this case, we are solving for capital R. So we let capital R be equals to small r raised to power m. Let's proceed to write down the characteristic equation, then determine the roots so we can tell whether it's a case of real distinct roots or is it complex or repeated for us to tell the general form of the solution. So we need r prime. We differentiate these, we get m r raised to power m minus 1. Capital R double prime will be m times m minus 1 r power m minus 2. We use these 3, we plug the 3 into our differential equation. R squared times capital R double prime, so that's R squared m into m minus 1 r raised to m minus 2 plus r times r prime, so r times m r to the m minus 1 minus lambda squared r minus lambda squared times small r power m equals 0. Again, if you combine the powers, for the first part, r squared times r raised to m minus 2 will give you r raised to power m. So we have m times m minus 1 times r raised to power m. For the second part, you have m r raised to power m minus lambda squared r raised to power m equals 0. Let's factor out the r raised to power m. R raised to power m into m minus 1 plus m minus lambda squared is equal to 0. R power m cannot be equal to 0. This is the auxiliary equation. We solve this for the roots. Solving m, let's first distribute the m in the first part. We will have m squared minus m plus m minus lambda squared equals 0. Minus m plus m is equal to 0, so this reduces to m squared minus lambda squared is equal to 0. Or simply m squared equals to lambda squared. And from here, our two roots are, our m is plus or minus lambda. So you can set m1 equals positive lambda, m2 equals minus lambda. So it's a case of real distinct roots. We will have our r1 equals x to the m1, and this is x to the lambda. I mean small r, Scotch U line r. R1 is small r raised to the m1, but m1 is lambda, so small r raised to power lambda. Our r2 is small r raised to m2, but m2 is negative lambda, so small r raised to minus lambda. The general solution is C1 R1 plus C2 R2. R is C1 R1 plus C2 R2. This is C1 R raised to lambda plus C2 R raised to negative lambda. We solve the second equation for the same case where k is positive. Remember, the general solution is given by, the solution is given by u is u of r and theta. So you have to solve for r, solve for theta, then take the product. It's given by the product r times r, theta, theta. So we have r, we proceed to solve theta for the same case where k is positive. Equation 2 is theta double prime plus k theta equals 0. K equals lambda squared would imply that this is equal to theta double prime plus lambda squared theta equals 0. If you solve this, what do you get? What are the roots for this equation? Cheryl? Is Cheryl in class today?
Yes.
What are the roots? Guess Paul? Is Paul present? Kisumu Central MP 2027. Is he present?
Yes, yes.
What are the roots?
Yes, still working it out.
Sorry?
Working it out.
Do you know how to solve a second order ordinary differential equation? You first need to write down the characteristic equation. I believe I took you guys through this. Mtu wa kwenda Japan. Are you done? Mr. Japan. SOO. Is he in class today?
Yes, I'm in class.
You done solving?
Yeah, kindly show us. Kidogo nimepotea.
This is a second order differential equation, just that it's given in theta. You guys are used to differential equations given in terms of the variables x and y. So you say, or let theta be equals to e to the, we've used lambda, mu what is theta prime? Mu e to the mu theta. Theta double prime is mu squared e to the mu theta. So theta double prime plus lambda squared theta becomes mu squared e to the mu theta plus lambda squared theta is e to the mu theta equals 0. factor out e to the mu theta. Mu squared plus lambda squared equals 0. The exponential function can never be equal to 0. So the auxiliary equation is mu squared plus lambda squared equals 0. We are trying to solve for mu. Mu squared equals minus lambda squared. Or mu squared equals minus 1 times lambda squared. If you take the square root both sides, mu is square root of minus 1 plus or minus square root of minus 1 square root of lambda squared. Mu is plus or minus I lambda. So here you are dealing with a case of complex roots. If you're dealing with a case of complex roots, so how does the general solution look like? Remember, this is an ordinary differential equation in the variable theta. So what will be our, say, theta 1, theta 2?
Theta 1 equal to cos lambda theta.
Theta 1 is cos lambda theta. Theta 2?
Sin lambda theta.
Sin lambda theta. The general solution?
C1 cos lambda theta plus C2 sin lambda theta.
Now, since we've already used C1 and C2 in solving equation 1, let's use C3, C4, because they are not supposed to be the same. So we can use C3 cos lambda theta plus C4 sin lambda theta. So for case 1, our U is the product it will be the product C1 r to the lambda plus C2 r is to minus lambda times C3 cos lambda theta plus C4 sin lambda theta. Are we at par? Can we proceed to case 2? Can I scroll down?
Excuse me. Where did you get the cosine and the sine?
If you solve an ordinary differential equation, then the roots of the characteristic equation turn out to be complex in nature. Then the general solution is given by a constant times cosine of something times theta plus. We went through this. Let me just do it one final time because 50 years need to be treated well.
Thank you.
If you're solving ax squared, if you're solving ay double prime plus by prime plus cy equals 0, you assume a solution y is e to the lambda x. You differentiate these, get y prime, get y double prime, plug into your differential equation. You'll notice that you end up with a quadratic equation where your lambda will be given by the formula minus b plus or minus square root of b squared minus 4ac divided by 2a. So this lambda can have 3 possible cases. Case 1, when square root of b squared minus 4ac is greater than 0, you'll have lambda 1 not equal to lambda 2. We call these real distinct roots. Remember, we started by assuming a solution y is e to the lambda x. If lambda 1 and lambda 2 are different, then you have y1 is e to the lambda 1 times x, y2 is e to the lambda 2 times x. The general solution is the combination of these two. Y will be c1 e to the lambda 1 x plus c2 e to the lambda 2 times x. B squared minus 4ac can be less than 0. Make that correction. It's not square root of b squared, it's b squared minus 4ac. Let me just scroll up. She's supposed to be b squared minus 4ac is greater than 0. If b squared minus 4ac is less than 0, then you will be dealing with a case of complex roots. Remember, to compute square root of a negative number, you introduce the fact that square root of negative 1 is equal to I. So you have this, if you have square root of minus b, you say this is square root of minus 1 times square root of positive b. Square root of minus 1 is I. Then square root of b evaluates to something finite. So if b squared minus 4ac is less than 0, then you have a case of complex roots, which will be in the form alpha plus or minus I times beta. This follows from, I said alpha, I wrote lambda, alpha plus or minus I beta. This follows from, you have lambda is minus b plus or minus square root of b squared minus 4ac divided by 2. But if you're dealing with a case of b squared minus 4ac less than 0, then you're having lambda is minus b plus or minus I times something. Let's assume that thing was, say, b, divide by 2. So your lambda will be equal to minus b divided by 2 plus I b, capital B, divided by 2. We choose to let the first part be represented by alpha, then b divided by 2, say, or let minus small b over 2 equals alpha, capital B over 2 equals beta. That's where the alpha, this was again, it is plus or minus, alpha plus or minus I times beta. So you'll have two values. You can set your lambda 1 to be alpha plus I beta, your lambda 2 to be equal to alpha minus I times beta. Remember, the solution is e to the lambda. So your y1 is e to the lambda 1, but lambda 1 is alpha plus I beta. Your y2 is e to the lambda 2, and this is e to the alpha minus I beta. But you start with an ordinary differential equation having real values, and then you're having solutions that are complex in nature. The presence of an I makes the solutions complex in nature, so that cannot be possible. You have to look for a way of arriving at a solution which is real in nature. So y1 is e to the alpha plus I beta. This is complex, but there's something we know. We know that we know lots of exponents. We can split these and say this is e to the alpha, e to the I beta. Still complex. Use Euler's formula. If you have e to the I theta, that is the same thing as cos. If you have e to the I theta, then it's the same thing as cos theta plus I sin theta. So we can expand the second part using Euler's formula. E to the I beta becomes cosine of beta plus I sine beta. Y1 is still complex in nature. Let's also rewrite Y2 using laws of exponents. E to the alpha minus I beta. It's e to the alpha e to the minus I beta. But again, if you have e to minus I theta, it's the same thing as cos theta minus I sine theta. So e to the I beta is, we have e to the alpha outside, then in brackets we have cosine of beta t minus I sine of beta t. You have y1 and y2. Y1 is e to the alpha t cos beta t plus I sine beta t. Y2 is e to the alpha t into cos beta t minus I sine beta t. Both are complex in nature, but if we rewrite them in this form, then we can do some algebraic manipulations such that we end up with real roots. By noticing that there's something we can do to these two equations. We can either add or subtract the two. For instance, if we add the two, then we have y1 plus y2 is equal to, we add these two. I sine beta t plus minus I sine beta t will go to 0. So this, we will have 2 of e to the alpha t cos beta t. Divide through by 2, divide through by 2. And you have a half y1 plus a half y2 equals e to the alpha t cos beta t. You take this as your first real solution. If you subtract the 2, then you have y1 minus y2. The cos beta t is what will vanish, so you'll have 2i e to the alpha t sine beta t. Divide through by 2i, divide through by 2i, and you arrive at your second real solution. Y2 is e to the alpha t sine beta t. The general solution y is given by c1 y1, so c1 e to the alpha t cos beta t plus c2 e to the alpha t sine beta t. So if you're solving a second order ordinary differential equation and the roots are complex in nature, this is how you give a general solution. Back to our theta double prime plus k theta, but we had set our k equals to lambda squared theta equals 0. After solving this, we found that our root mu was equal to plus or minus I times lambda. This is complex. Remember, plus or minus I lambda is the same thing as 0 plus or minus I times lambda. So that's to tell you your alpha is equal to 0, your beta, because the root is alpha plus or minus I beta. So your beta is equal to lambda. So the solution will be e to the alpha times something. In this case, we're dealing with theta. So you'll have C1, in this case C3, because we had already used C1, C3 e to the alpha, but alpha is 0. Cosine of beta times something, beta times theta, beta is lambda, plus C4 e to the alpha theta, alpha is 0, 0 times anything is 0, sine of lambda theta. But again, e raised to 0 is 1, so you just end up with C3 cos lambda theta plus C4 sine lambda theta. Hope that is clear now. Does it make any sense now?
Yes.
We go to case 2, where k is less than 0. K equals to minus lambda squared. Our two equations, the first equation will be r squared r double prime plus small r prime minus k times r, but k is minus lambda, so becomes plus lambda squared r equals 0. This is Cauchy-Euler. We have to write down the auxiliary equation. R is small r to power m. R prime is m r to the m minus 1. R double prime is m times m minus 1 r to the m minus 2. Using r prime and r double prime in our differential equation. What is the characteristic equation, or the auxiliary equation in this case? You guys have 1.5 minutes to tell me the answer.
M squared minus lambda squared is equals to 0.
Is it minus or plus?
Plus
The auxiliary equation is m squared plus lambda squared equals 0. M squared plus lambda squared is equal to 0. So what is m?
plus or minus I lambda.
So you're solving Cauchy-Euler and it's a case of complex roots. Maybe you need to say m is equal to alpha plus or minus I beta. Alpha equals 0, beta equals lambda. The general solution for complex we started this class by giving a summary of what happens if you're solving ax squared y double prime plus bx y prime plus cy equals 0. And the roots are complex in nature. The general solution is x to the alpha into c1 cos beta ln x plus c2 sin beta ln x. But here it's Cauchy-Euler in R. So the general solution will be, in place of x, you substitute with R. So I need you guys to tell me the solution for this differential equation.
C1.
No, the general solution is x to the alpha. So you're starting from x to the alpha, not C1.
X per 0 is 1.
Why are you still having an x? We are dealing with Cauchy-Euler in R.
R per 0 is 1.
So the general, just a sec, solution for Let me just write this before you tell me. R squared R double prime plus R prime plus lambda squared R equals 0 is R to the
Power 0
R power 0
to brackets C1
We've already used C1 up to
C
C4,
C5
C5,
yeah, cos lambda ln plus C6 sin.
sin lambda ln. We had to write this first for the sake of your colleagues. Some will not be able to tell that R power 0 was 1. So that's why we couldn't jump straight to, the contents inside the brackets. We have to illustrate for them. C6 sin lambda ln R. We solve theta. We solve for theta for the case where lambda is, where k is less than 0. So we'll have theta double prime. Maybe I should say equation 2. Theta double prime minus lambda squared theta equals 0. The auxiliary equation is mu squared minus lambda squared equals 0. Mu squared equals lambda squared. Mu equals plus or minus lambda. So real distinct. So what is theta in this case?
Theta 1 is equal to e power lambda theta. E power negative lambda theta.
The general
Theta is equal to C7 e power lambda theta plus C8 e power negative lambda theta.
Hii coffee imepoa. If you boil it for me, it will not change your gender. Please, please. Are we together?
We are.
Thank you.
We are with us.
You are with us. Mtusi. Nisikize tu kidogo kidogo, you find your gender has been. Tambia watu ni. You listened to this young. Wait, wewe unajua ni class. Am I back in the meeting? Graduates to be. Am I back in the meeting? What was the last thing? I don't know. Had I given the general solution of theta? Naona haija change your gender. Thank you. Had I given the general solution for theta as C7 e to the lambda theta plus C8 e to the minus lambda theta? Had you written this?
No.
No. Just like
This
back
is the general solution. Because the auxiliary equation was, if you solve, had I written the root, mu is plus or minus lambda.
Rudy kidogo, it's a bit back.
We can only, I lost that. Can only start afresh from, but had I written the auxiliary equation, mu squared minus lambda squared equals 0. Had we written this?
Yes.
Yeah, just from now you can.
So if you solve this, then you get mu is plus or minus I lambda. Theta 1 is e to the lambda 1 times theta. No, e to the mu 1 because is e to the mu 1 times theta. From here, you can choose your mu 1 to be, it's not complex. If you solve mu squared equals lambda squared, then this is the same thing as mu squared equals positive lambda squared. So mu is plus or minus lambda. So you can set your mu 1 to be positive lambda, your mu 2 to be minus lambda. So theta 1 is e to the mu 1 theta. This is e to the lambda theta. Theta 2 is e to the mu 2 theta. This is e to the minus lambda theta. The general solution is C1. No, we are picking up from C6. So we'll have C7 e to the lambda theta plus C8 e to the minus lambda theta. You can form your capital R of R, theta of theta by taking the product. What was our R? C5 cos lambda ln R plus C6 sin lambda ln R. This quantity times C7 e to the lambda theta plus C8 e to minus lambda theta. Are we at par? Can we move to the final case?
Yes.
So we go to case 3 where k is equal to 0. Case 3, k equals 0. Equation 1 becomes r squared r double prime plus r prime equals 0. What is the auxiliary equation? That is the first equation. Equation 2 becomes theta double prime equals 0. So we need to solve these two. Take the product of the two solutions. We'll have the general solution for the third case. But we start with the first one. R squared r double prime plus small r capital R equals 0. What is the auxiliary equation for this DE?
M squared is equals to 0.
Sorry?
M squared is equal to 0.
The auxiliary equation is m squared equals to 0. m1 is equal to m2 is equal to 0. It's a case of repeated roots, right? When m squared is equal to 0, you can only have the value m equals 0. No other way out. Repeated roots. If you have repeated roots, if you're dealing with cotula in x, y1 is x to the m, y2 is we wrote this x to the m ln ln x. If it's cotula in x, this is cotula in R, where m is repeated, the root is equal to 0. So what will be our R1, R2?
R1 is equals to R power 0.
R1 is R power 0. R2 is
R power 0 ln R.
ln R. But R power 0 is 1, so this is R1 is equal to 1. R2 equals ln R. We need the general solution. It's a combination of these two. So capital R will be given by, we're picking up from C8.
C9 plus C10 ln R.
We solve theta double prime equals 0. This one should be easy. If theta double prime is equal to 0, what is theta? Okay, let's do this step by step. If the second derivative is equal to 0, what is the nature of the first derivative?
C11 constant.
Constant.
So we use C11 in this case, right?
Yes.
So what will be theta?
C11 theta plus C12.
What is U? R times theta C9 plus C10 ln R times C11 theta plus C12. Okay. Let's look at cylindrical coordinates. Solution of the Laplace equation in polar coordinates.
Excuse, madam.
Sorry?
Yes, good morning.
Morning.
Yeah. Some of us have not even taken breakfast. Maybe you can give us 5-minute break and we continue from there.
Are you sure 5 minutes is enough?
Yeah, maybe then they can be 10 because now we hatutaki kuachwa nyuma, tunaandika na speed sana, hatuwezi anza shika kitu ingine kando na pen.
Okay, meet at 9:20.
Okay, thank you.
Watu people from the home of the next DP, mmemaliza kunywa chai? Hmm? Marigu Moses. Are you done? Don't think he's back in the meeting. You can tell him the class is officially resuming.
Carry on and
We look at solution of the Laplace equation in cylindrical coordinates. The Laplacian nabla squared u equals 0. In cylindrical coordinates, it's given as 1 over r partial r, r partial u partial r, plus 1 over r squared partial squared u partial theta squared, plus partial squared u partial z squared equals 0, which is equivalent to, if you apply product rule to the first part, partial squared u partial r squared plus 1 over r partial u partial r plus partial squared u partial theta squared plus partial squared u partial z squared equals 0. Let's first derive before solving. So in cylindrical coordinates, the coordinates are r, theta, and z. Here we have r is equal, x is equal to r cos theta, y equals r sin theta, and z is just equal to z. Maybe I should.
Excuse me. Can you scroll back a bit? Yeah, right there. Done.
So we are changing from Cartesian coordinates to cylindrical coordinates using the transformations x equals r cos theta, y equals r sin theta, and z is just equal to itself. So yeah, we need because the 3D the Laplacian in 3D in Cartesian coordinates is given as partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared equals 0. So we will need these expressions in cylindrical coordinates. We first write partial u partial x, partial u partial y, partial u partial z in cylindrical coordinates. Once we have these ones, then to obtain the second partial derivatives will be easy. We need them in cylindrical coordinates. We need to write those partial derivatives in cylindrical coordinates. So notice we are starting from u as a function of x, y, and z to u as a function of r, theta, and z. U is a function of 3 variables, so to obtain the partial derivatives, we will use chain rule 3 times. We start with partial u, partial x will be partial x of u, which is a function of r, theta, and z. You can always check on my speed. So this will be partial u, partial r, the first component, partial r, partial x, plus partial u, partial theta, partial x, plus partial u, partial z, partial x. Similarly, our partial u, partial y will be partial y of u, which is a function of r, theta, and z. This will be given as partial u, partial y, partial u, partial r, partial r, partial y, plus partial u, partial theta, partial y, plus partial u, partial z, partial y. partial u partial z. Since z is equal to itself, it will just be the same thing as partial u partial z, but there's no harm in using chain rule. This is partial z of u, which is a function of r, theta, and z. This is equal to partial u partial r partial z plus partial u partial theta partial z plus partial u partial z partial z. So let's start with partial u partial x. Partial u partial x. Maybe we can write this again. X is equal to r cos theta. Y is r sin theta. X squared plus y squared is equal to r squared, or equivalently, square root of x squared plus y squared is equal to r. And finally, theta is equal to tan inverse of y upon x. So to get partial u partial x, it's partial u partial r partial x plus partial u partial theta partial x plus partial u partial z partial x. We also need to indicate that z is equal to itself. So we need partial r partial x partial theta partial x partial z partial x. Partial r partial x is the partial derivative with respect to x of our r is square root of x squared plus y squared. Can write this as partial x of, so we can write this as x squared plus y squared raised to power a half. To differentiate this, we pre-multiply by the power, which is a half, then multiply by the original function, decrease the power by half, so half minus 1 gives negative half, then multiply by the derivative of whatever is inside the brackets with respect to x, so times 2x. This is equal to these two.
Excuse me, madam.
Sorry?
You feel gone too fast.
Okay, you need to be checking on my speed. So I scroll up to what part? You need to tell me. Do you have this?
No, I didn't take that. Yes, there. Scroll down. There. We are good to go.
So the 2 in the denominator cancels out with the other 2 in the numerator, and we have x squared plus y squared raised to minus half times x. So x squared plus y squared raised to negative half can also be written as 1 over x squared plus y squared raised to positive half times x. But this is equal to x over something raised to power half is the same thing as square root of, so square root of x squared plus y squared. So this is partial r, partial x, but we know that x is given as r cos theta. We also have that x squared plus y squared is r squared, so if we take the square root of that, we get r. So this is equal to x is r cos theta. Square root of x squared plus r squared is r. R and r cancel out, and we have this is equal to cos theta. So we have partial r, partial x equals cosine of theta. Can also obtain partial theta, partial x. This is the partial derivative with respect to x of theta, but theta is equal to tan inverse of y over x. So the derivative of arctan is given as 1. Arctan f of x is 1. Let me just remind you, again, there's no harm in reminding you severally that dx of tan inverse of a function f of x is given as 1 divided by 1 plus f of x, the whole thing, the whole function f of x squared times d dx of f of x. So when you're using partial derivatives, you only need to change the symbol from total derivative to partial derivative. So partial derivative with respect to x of tan inverse of y over x will be 1 divided by 1 plus our function here is y over x. So 1 plus y over x, the whole thing squared times partial x of y over x. If we differentiate y over x partially with respect to x, we treat y as a constant. So you factor out y, differentiate 1 over x with respect to x, you get minus 1 over x squared. So this will give us minus y over x squared divided by 1 plus y squared over x squared. If we combine everything in the denominator so that we have a common denominator, we have minus y over x squared divided by x squared plus y squared over x squared. You guys can check on my speed. Hope I'm not too fast. So notice that there is an x squared that is going to cancel out in both the numerator and the denominator. This and this will cancel out. And you have minus y over x squared plus y squared. This is minus y is r sine theta. Divide by x squared plus y squared is the same thing as r squared. So this is minus r sine theta divided by r squared. We have one of the r's will cancel out, and you remain with minus sine theta divided by r. Next, we need partial z, partial x. This is the partial derivative with respect to x of z, which is just equal to z. When you differentiate z partially with respect to x, you treat it as a constant. So this gives you a 0 because the derivative of a constant is equal to 0. Now we are good to write our partial u, partial x in cylindrical coordinates. So partial u, partial x, which is partial u, partial r, times partial r, partial x. We've found our partial r, partial x to be equal to cosine of theta, plus partial u, partial theta, times partial theta, partial x, partial theta, partial x is minus sine theta over r, plus partial u, partial z, times partial z, partial x is 0. So we get our partial u, partial x is equal to cos theta, partial u, partial r, minus sine theta over r, partial u, partial theta. You can tell me if we are at pass, so we move on to evaluating partial u, partial y. Can we move to partial u, partial y?
Yes.
Partial u, partial y is partial u, partial r, partial r, partial y, plus partial u, partial theta, partial theta, partial y, plus partial u, partial z, partial z, partial y. We need partial r, partial y, partial theta, partial y, as well as partial z, partial y. So we start with partial r, partial y. Partial r, partial y is the partial derivative with respect to y of our r is x squared plus y squared raised to power half. This is a half times x squared plus y squared raised to minus a half times the derivative of x squared plus y squared with respect to y, so times 2y. This is equal to, we can cancel out these two. So we have x squared plus y squared raised to minus half times y. This is equal to y divided by square root of x squared plus y squared. But y is the same thing as r times sine theta. X squared plus y squared, square root of x squared plus y squared is the same thing as r. So r and r cancel out. And we have partial r, partial y equals sine theta. Next, we compute partial theta, partial y. This is the partial derivative with respect to y of theta, but theta is tan inverse of y divided by x. So this will be 1 divided by 1 plus y squared over x squared times partial y of y over x. If you differentiate y over x partially with respect to y holding x constant, what do you get? What is partial y of y over x?
1 over x.
So you get 1 over x. If we combine terms in the denominator, we have x squared plus y squared over x squared. What does this simplify to? What does this reduce to?
X squared plus y squared.
X?
X over x squared plus y squared.
But x is the same thing as r cos theta. X squared plus y squared is the same thing as r squared, right? Cancel out r and r, you get cos theta divided by r. So we have partial theta partial y is cos theta over r. We need partial z partial y. This is the partial derivative with respect to y of z is just equal to itself. So differentiate y, z with respect to y, treat it as a constant, get 0. So we can now give an expression for partial u partial y. Partial u partial y will be partial u partial r times, what is our partial r partial y?
Sin theta.
Plus partial u partial theta partial y
Cos theta over r.
plus partial u partial z partial y 0. So this is equal to sin theta partial u partial r plus cos theta over r partial u partial theta. We need partial u partial z. It's partial u partial r partial z plus partial u partial theta partial z plus partial u partial z.
Excuse me. Could you kindly scroll up a little bit?
To which part?
The previous step, the one we've just written, not that far. There. Up. There.
This thing is 0. Partial u partial z times 0. Partial z partial y is 0. So this is partial u partial r times sin theta, partial u partial theta times cos theta over r, partial u partial z times 0. Hope it's clear. Let me know when you're done.
It's okay, we can proceed.
So we now need an expression for partial u partial z in cylindrical coordinates. We need partial r partial z, partial theta partial z, as well as partial z partial z. Partial r partial z is the partial derivative with respect to z of r, but r is x squared plus y squared raised to power half. What do you get?
Zero.
This is equal to 0. We also need partial theta partial z. It's the partial derivative with respect to z of theta is tan inverse of y over x. What is this equal to?
0.
Next, we need partial z partial z. Partial z partial z. Partial derivative with respect to z of our z. If you differentiate z with equal to itself, get 1. Oh, the screen is glitching. Okay, it's working. Let me check. Partial u partial z is partial u partial r times partial r partial z is 0 plus partial u partial theta times partial theta partial z is 0 again plus partial u partial z times partial z is 1. 0 plus 0 plus partial u partial z. So it's equal to itself, partial u partial z. Now we have partial u partial x, partial u partial y, as well as partial u partial z. We need partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared equals to 0. So let's start with partial squared u partial x squared. Notice that this is the same thing as partial derivative with respect to x of partial u partial x, right? So you can either choose to proceed by just deducing your partial x as an operator, then square that thing, get your partial y, square it to get partial squared partial y squared. At the end of everything, define the Laplacian on your function u. Or you can proceed by noticing that partial squared u is the same thing as the partial derivative with respect to x of partial u partial x. So you get your partial x from partial u partial x, get that product, get the product of partial x and partial u partial x. So you go straight to partial squared u partial x squared. Same thing to partial squared u partial y squared. Set it equal to the partial derivative with respect to y of partial u partial y. Go to partial squared u partial z squared. Set it equal to the first partial derivative, to the partial derivative with respect to z of the first partial derivative of u with respect to z. Then add the 3. So from partial u partial x equals to, what was our partial u partial x again? For those who are following,
cos theta partial u partial r minus sin theta over r partial u partial theta.
From this, we have partial u partial x is that thing, so we can deduce our partial x as cos theta partial r minus sin theta over r partial theta, right? Is that okay? We're just removing the u. If partial u partial x is then partial x is this. So if partial squared u partial x squared is equal to partial x of partial u partial x, then this is equal to, this is partial x and this is partial u partial x. Maybe I can write this down. It's equal to cos theta partial r minus sin theta over r partial theta times partial u partial x. Partial u partial x is cos theta partial u partial r minus sin theta over r partial u partial theta. Hope we are together. Now we want to expand this bracket. This is equal to, we first take cos theta times partial r into the second bracket, cos theta partial u partial r minus sin theta over r partial u partial theta minus sin theta over r times cos theta partial u partial r minus sin theta over r partial u partial theta. We can expand the brackets further. So for the first part, we distribute the cos theta times partial r. For the second part, we also distribute minus sin theta over r. So let's start with the first bracket. It's going to be cos theta.
Excuse. You've written sin theta over r in this previous step. It's incomplete. It's supposed to be a
partial theta.
Yes.
Thanks for that observation. We have a partial theta here. So if we distribute cos theta partial r in the first bracket, what do we have? So this is into cos theta partial u partial r minus cos theta partial r of, we have sin theta over r partial u partial theta. Let's distribute the minus sin theta over r in the second bracket. Minus sin theta over r times partial theta of cos theta partial u partial r minus we have a plus sin theta over r times partial theta of sin theta over r partial u partial theta. So once we have this, we now look at we now apply product rule where applicable, but before applying product rule, we factor out any constants. So if we start with the first term, cos theta, then we are taking partial r of cos theta times partial u partial r. What can we factor out as a constant? So for the first bracket, we factor out a function which is not a function of r. For the second part, same thing. For the last two, we factor out anything that is not a function of theta. So what do we get? We can choose a different pen. What do we factor out from the first bracket?
Cos theta.
So cos theta times another one, we have cos squared theta. I think this one can just be simplified in one step. Partial r of partial u partial r is partial squared u partial r squared, right? For the others, we can do the simplification in a number of steps. So from the second bracket, what do we factor out?
Sin theta.
So cos theta, we factor out sin theta, then we are left with partial r of 1 over r partial u. It's partial u partial
theta.
From the third bracket, we're not factoring out anything. Minus sin theta over r partial theta of cos theta partial u partial r, because we can differentiate the first derivative. From the last bracket, what do we factor out?
1 over r.
So we have sin theta over r times 1 over r partial theta of sin theta partial u partial theta. If you apply product rule to the second bracket, what do you get? Maybe let me write down the first term first. So this is equal to cos squared theta partial squared u partial r squared minus cos theta sin theta. If you apply product rule, what do you get?
Excuse, madam, we can't see your pen.
Can you read for me the last line that you're able to see from your end?
We were the last bracket is what we were trying to.
You mean sin theta over r times 1 over r partial theta of sin
Yes,
theta?
on my end, the last thing that I can read is sin theta of r. I don't know from the other guys.
Excuse me, madam.
Yes.
Could you kindly share today's notes, because I've realized we've been having terrible internet, so some of us have actually been missing out on some notes.
Is it from my end or your end?
It's on our end. It's not on your end.
Okay. Is there anyone who is able to see beyond sin theta over r?
It's fine.
Yeah, I can see now.
Okay. Can we proceed? So if you differentiate 1 over r partial u partial r with respect to r, differentiate 1 over r holding partial u partial theta constant plus differentiate partial u partial theta holding 1 over r constant. What do you get?
1 over r partial u partial over 1 over partial u partial r partial theta minus
1 over r squared
partial u partial theta
partial theta plus 1 over r partial squared u partial r partial theta, right?
Yes.
Let's move to the third bracket. Outside we have minus sin theta over r. Then let's apply product rule. Differentiate cosine holding partial u partial r constant, then differentiate partial u partial r holding cosine constant. What do you have? If you differentiate cos
minus sin theta
minus sin theta
partial u partial r plus cos theta partial squared u over partial theta partial r.
move to the last bracket. We have sin theta over r squared outside plus sin theta over r squared into, if you apply product rule, let me scroll up just a little bit. We are differentiating sin theta partial u partial theta with respect to theta. Differentiate sine holding partial u partial theta constant, then differentiate partial u partial theta holding sine constant. Tell me what to write. Let me scroll down. What do we have here?
Cos theta
Cos theta
partial u partial theta
partial u partial theta
plus sin theta partial squared u over partial theta squared.
So if you expand the brackets further, what do you get? For those who are requesting for their notes, I have not written them down. We're just solving with you guys. So I'll try to do a write-up of the same and send. I don't have to keep on scrolling up and down. For those who are following, you can tell me what to write. You know, the first term is cos squared theta partial squared u partial r squared. The next term, what do we have? For those who are following,
Plus cos theta sin theta.
plus
Yes.
cos theta
Sin theta over r squared. Partial u partial theta.
partial u
Partial theta.
next term,
Minus cos theta sin theta over r.
my screen is misbehaving. Just a sec. Yeah, it's okay now. Plus
Minus cos theta sin theta over r. Partial squared u over partial r partial theta.
next term,
Plus sin squared theta
over
r. Partial u partial r.
next,
Minus sin theta cos theta over r. Partial squared u partial theta partial r. And plus sin theta squared over r squared. Partial squared u partial theta squared.
Are we done?
And plus sin theta cos theta over r squared.
Plus sin theta cos theta
over r squared. Partial u partial theta.
We're good?
Yes.
We now collect like terms. I can see there's a minus cos theta sin theta over r, then the mixed partial. There's another minus sin theta cos theta over r. These two are the same. Sorry?
Would you scroll up a bit?
Okay.
Up
Is that
there,
fine? Okay. We can use different pens to indicate like terms. Is there another partial u partial theta, a term that looks like this? Let me pick a different pen. Cheryl, is there another term that looks like this?
No.
We don't have it?
Oh, we have.
Okay, so it's here, the last one. So the terms in green are similar, those in red. Any other like terms? I can use a different pen to Do you have any other? Maybe let me just scroll up. They are the only ones, right?
Yes.
Can I scroll down?
Yes.
So collecting like terms and simplifying, what do we get? Of course, the first term is cos squared theta partial squared u partial r squared. We have 2 sin theta cos theta over r partial u partial theta. Then we have minus 2 sin theta cos theta over r. Then the mixed partial, right? Then the rest remain the same. Can you tell me the other terms?
Sine squared theta over r.
Sine squared theta over r.
Partial u partial r. Plus sine squared theta over r squared. Partial squared u over partial theta squared.
So that's partial squared u partial x squared. We go to partial squared u partial y squared. Partial squared u partial y squared is partial y of partial u partial y. Use our partial u partial y to extract partial y, then we do the product. What was our partial y? I hope I'm not too fast. Let me just scroll up just in case there's somebody who is still copying. Are we at par? Are we good? Can we proceed? Wait, am I still in the meeting?
Yes.
Can we proceed?
Yes.
What was our partial u partial y?
Sine theta partial u partial r plus cos theta over r partial u partial theta.
From here, what is our partial y?
Sine theta partial r plus cos theta over r partial theta.
So partial squared u partial y squared is partial y of partial u partial y. This is equal to partial y is sine theta partial r plus cos theta over r partial theta partial u partial y. It will not fit. Need to rewrite this. This is sine theta partial r plus cos theta over r partial theta times sin theta partial u partial r plus cos theta over r partial u partial theta. So we expand this. This is equal to sin theta partial r into the second bracket, sin theta partial u partial r plus cos theta over r partial u partial theta. Then we'll have cos theta over r plus cos theta over r partial theta of sin theta partial u partial r plus cos theta over r partial u partial theta. Giving time for those who are still coping. I think we can now proceed. Which is equal to sin theta partial r into sin theta partial u partial r plus we are distributing sin theta partial r into cos theta over r partial u partial theta. Next, we distribute cos theta over r partial theta in the second bracket. Plus cos theta over r partial theta of sin theta partial u partial r plus cos theta over r partial theta of cos theta over r partial u partial theta. So we now begin the process of factoring out whatever is constant before we apply product rule. For the first bracket, it automatically simplifies to sine squared theta partial squared u partial r squared. Would we factor out as a constant from the second bracket? What do we factor out?
Cos theta.
Factor out cos theta. So here we have sin theta, cos theta, partial r of 1 over r partial u partial theta. From the third bracket, what do we factor out? You guys following?
Yes.
Maybe I can give
We
you
are
some.
tired.
No, we have to finish this. We're just deriving, doing the derivation, and then we'll pick it up from solving in our next class. So we have to finish this. You have 3 minutes to factor out all the constants, apply the product rule, and then tell me the answer.
Okay, it's cos theta over r.
Sorry?
Cos theta over r.
Just a sec. I hope my screen is okay. Cos theta over r. Uh-huh. Are you muted unknowingly?
Of partial theta of sin theta partial u partial r. Plus cos theta over r squared partial theta of cos theta partial u partial theta.
What do we get?
We get sin theta, sin squared theta of the second derivative of partial u partial r plus sin theta cos theta into bracket 1 over r partial u partial r partial theta.
Partial squared u, partial r, partial theta.
Not partial squared u. Not partial squared u.
Not
Partial u.
partial u. Then
Yes,
it's
partial
not 1 over r. It's not 1 over r. It's not supposed to be 1 over r. I thought you had differentiated partial u, partial theta first, holding 1 over r constant. Then this doesn't, this is not 1 over r. Derivative of 1 over r is not 1 over r.
Okay, for the derivative of 1 over r is negative 1 over r squared.
Yeah, that's correct. Partial u, partial theta.
Partial theta, yes.
Plus.
Okay, yeah, minus. Okay, plus partial squared u of partial r partial theta.
We have a 1 over r here.
Yes.
So we need a 1 over r here. We're holding 1 over r constant, then we differentiate partial u. We proceed to the next term.
Yes, plus cos theta over r. Into bracket cos theta partial u partial r plus sin theta partial u squared partial theta partial r.
Proceed to the final bracket. Plus
cos theta over r squared
into
of cos theta partial u squared partial theta squared minus sin theta partial u partial r partial theta.
Further expansion or simplification.
Okay, we get sin theta, sin squared theta partial u partial r squared plus sin theta cos theta over r partial u squared partial r partial theta
It is not
minus
visible. Let me just scroll. Just a minute. This is partial r partial theta.
minus sin theta cos theta over r squared partial u partial theta plus cos squared theta over r partial u partial r plus sin theta cos theta over r partial squared u partial theta partial r plus cos squared theta over r squared partial squared theta partial u squared over partial theta squared
Collect like
minus
terms. Oh, minus
minus sin theta cos theta over r squared partial u partial theta.
collect the like terms and simplify.
We have sin squared theta partial u partial r squared plus 2 sin theta cos theta partial u partial r squared partial r partial.
Is it over r?
Yes.
Partial.
partial squared u partial r partial theta and then minus 2 sin theta cos theta over r squared partial u partial theta and then plus cos squared theta over r partial u partial r plus cos squared theta over r squared partial u squared partial theta squared.
Next is we need partial squared u partial z squared. It's partial z of partial u partial z. But partial u partial z was equal to itself, right? So this is just partial squared u partial z squared. So adding partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared. Need to add those three. What was our partial squared u partial x squared? Maybe let me just indicate that partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared is equal to, what was our partial squared u partial x squared?
Cos squared theta
Cos squared theta
partial u partial r squared plus 2 sin theta cos theta over r partial u partial r minus sin theta cos theta
minus 2 sin theta cos theta.
Yes. Over r partial
Is it-
squared u
Is it R or R squared?
r. It's r.
Which one has an R and which one has an R squared?
They all have r's.
Okay. The R?
Okay, it's fine that way. And then partial squared u, partial r, partial theta.
Partial R, partial theta.
Plus sin squared theta over r. Partial u, partial r. Plus sin squared theta partial over r squared. Partial squared u, partial theta squared. And then for partial u, partial y, we have sin squared theta partial u, partial r squared. Plus 2 sin theta over r.
2 sin theta cos theta.
Yeah, sin theta cos theta over r.
Hmm.
Partial u, partial u squared plus partial r, partial theta. Minus sin theta cos theta over r squared. Minus 2 sin theta cos theta. Sorry. Partial u, partial theta.
Then it means we need to change something. R squared u theta. This is supposed to be R squared. This is theta. Must have made a mistake. We proceed.
Okay, plus cos squared theta over r. Partial u, partial r. Plus cos squared theta over r squared. Partial squared u, partial theta squared. And then plus theta u plus partial u squared plus over partial z squared.
If you simplify this, try to cancel out any like terms with opposite signs. 2 sin theta cos theta over r, partial squared u, partial r, partial theta. Do we have a minus 2 sin theta cos theta over r, partial squared u, partial r, partial theta?
Yes.
So they'll cancel out. Any other thing? Okay, if you cancel out like terms of opposite signs, what do you end up with? Let me just try to scroll up. I can use this. Is there a term that looks like this?
Okay, we'll end up with cos squared theta partial u, partial r squared.
Just a sec, let me scroll down. So cos squared theta
partial u, partial r squared plus Sine squared theta partial u partial r squared
plus
sine theta over r partial u partial r
sine theta over r
sine squared theta, sorry.
sine squared theta over r partial u partial r
Plus cos squared theta over r partial u partial r
plus
and then plus sine squared theta over r squared partial u squared plus over partial theta squared
plus cos squared.
yes
Plus
partial u partial z
partial
squared.
squared u partial z squared. Factor out what is common. Use the identity that cos squared plus sine squared is 1. What do you get? Cos partial squared u partial r squared from the first two, right? We know that cos squared plus sine squared is equal to 1, right? So if we factor out partial squared u partial r squared from the first two terms, this is what we get, right?
Yes.
Factor out what is common from the next two terms. Use the identity sine squared plus cos squared is 1. What do we get?
1 over r partial u partial r.
The next two.
1 over r squared partial u partial
Squared u partial theta squared.
yes.
Finally, partial squared u partial z squared. So we'll pick it up from here in our next class. We'll now solve this by method of separation of variables.